Two long parallel wires fixed in space carrying currents I1 and I2. The force of attraction is F. What currents will give the attractive force of 4F? Okay, so we have two wires, and when do they attract? When they go in the same direction or opposite direction? Same? Let's find out. What's the magnetic field like around this wire?
This coming out of the top and at the bottom.
Out of the top and into the bottom, right? So out and in. So let's draw our other wire down here, and if it's to the right, then what kind of force does the brown wire get from the green magnetic field?
Down.
Down. Wait, what?
Okay, hold on. The field is coming out and current's in, so it's a force downward. Yeah.
No, it's up. The field is going up.
Oh, it's going in? Okay, then it's up, yeah. Force up. So it's fine.
Hey, there's no substitute for practice. Current this way, B field in, so it's going to be up. So this one gets a force up. Oops. So therefore, the green one should get a force
Down.
down. Okay, so they attract, right? All right, so yeah. So what's our equation for this?
Force is equal to BLI.
Right? But where's the magnetic field coming from? It's coming from this wire, right? And how do we find magnetic field around a wire?
That's equal to
Mu naught over 2 pi I over R. So that's that part, right? And then we've got I, L, sine theta. Right? Now the way they write it normally is they write the whole thing like this. Magnetic field for a wire, or magnetic force on a wire from two wires. They put the L over here usually, and then they have mu naught over 2 pi I1, I2 over, usually they write D, the distance between the wires. Okay, you can put R, and the sine theta, R sine theta is 1, right? Because we have a 90-degree angle. Okay, so if I want 4 times the force, what do I have to do?
Double
Double each current.
I could double each current. That'd do it. Is that one of our answers?
Yes.
Yes, so that's answer choice D. All right? Okay, let's go to our next one. Number 47. You have this magnetic field. And you have this wire. And they want to know the force on the wire. Which way is the force on the wire?
To the right.
Current up.
Well, my thumb is pointing.
Right hand rule or left hand rule?
Right hand.
Right hand rule.
Left hand opposite rule.
Change the signs here.
The answer is C. Direct it to the right. Excellent. Okay, number 19. The answer is to the right. Okay, number 19. We got this one where we have a current here and a current here. And they want to know, on the line in between them, where is the magnetic field 0?
No place.
Why not?
Because they're moving in the opposite.
Because this one gives you a magnetic field that's
Downward.
this way, right?
And
And this one
Also
gives you a magnetic field that is
down.
this way.
Counterclockwise.
this way, which is also downward. So what happens in between the two?
No matter what,
Yeah, no matter what, it always adds up, right? So our answer is E. At no points does the B field ever cancel out. Okay, now we get to a harder one. Well, not harder, it's just newer. Here's my magnetic field. And now I have a loop O wire that looks like this, that has a length here of L from here to here, and I'm going to take this thing, I'm going to move it to the right at a velocity v. So I'm going to take this loop of wire and I'm going to pull it out of the magnetic field. And I want you to notice my magnetic field is in this region only. Okay, now in the real world there would be some gradual change from one to the other probably, but we have a nice distinct line where the magnetic field ends. Okay? So when I move this to the right, all right, do we have, first of all, do we have flux? What's flux?
Yes, we do. Yes, we do.
Magnetic flux is VA cosine theta. Do I have a magnetic field inside my loop?
Yes.
Check. Is there an area through which it goes through in the loop?
Yes.
Check. Do we have an angle so that we have something other than 0?
Yes.
Yeah, because technically my angle is
Perpendicular.
0 degrees. It's perpendicular. Well, the vector goes perpendicular through, so it's angle of 0 with the area vector. Therefore, my cosine of theta is 1. So, when you pull this to the right, do you have a change in flux?
Yes.
Which one's changing?
The area.
The area is changing. Is the area increasing or decreasing? It's decreasing. So the area is decreasing, therefore my flux is decreasing. Now remember, Faraday's law said if you have a change in flux with time, you would create an EMF. And Lenz's law says that this EMF is going to be such that it makes a current that will produce its own magnetic field that tries to stop or hinder or oppose the change in flux. Okay? So what's happening to my flux? Is my flux getting bigger or smaller?
It's getting smaller.
My flux is getting smaller. So therefore my EMF in my wire, my virtual battery, is going to get set up to produce a current that will try to hinder or oppose this decrease in flux. So my flux is which way? Into or out of the board?
No, into.
Into the board. So how can this wire produce its own current to produce more flux into the board to oppose the decrease? You say clockwise? Let's find out. If the current goes clockwise around, the current goes clockwise around, how will it set up a magnetic field inside the loop? Out of or into the board?
Into the
Here's how you do it. There's an easy way. Stick your thumb in the direction of the current, grab the wire. And your fingers, do they go into the board on the inside of the loop? Or do they come out of the board? Into the board. Now look, no matter where you grab it, you get the same thing. It goes in, it goes in, and if you grab it up top, it goes in, right? So if it goes clockwise, you're going to get this.
So it's not going to.
So, is the brown magnetic field?
Fingers are going into.
Hey, by the way, there's another kind of slick way.
These fingers are going
You're looking for what's
Okay. So what's happening to my blue magnetic field?
increasing.
Is it increasing or decreasing?
Increasing.
My blue magnetic field actually isn't changing at all, but the area is decreasing, right? So my flux is decreasing. So my flux into the board is decreasing. So if I add this brown magnetic field, will that try to keep the flux as it was? Yeah, right? It will, won't it? So that's the correct answer. It will go clockwise.
Basically, we're creating more air.
So I was right.
You're right. That's a really challenging problem. So it takes about 4, 5, or 6 steps to get that right.
Okay, wait. Okay, so you're saying that by adding more field going in, you're either increasing the area or increasing the magnitude in that small area.
you're increasing the overall
Area.
flux.
Okay, the overall area.
Because not only you're increasing the area, but you're increasing the magnetic field in,
Okay, all right.
right? So you're trying to counterbalance the decrease in flux. Okay? Now, the next question is, and this is new, it says, if we say clockwise, then our answers are either A or C. But the question is which one? They want to know the magnitude of the current, right? Current or EMF?
Current.
Magnitude and direction of the current, okay? How do you find current?
Charge over.
EMF overall.
Yeah.
It's V equals IR, or in our case, I equals EMF over R. They give you the resistance of the wires R, right? So we have to find the EMF. How do we find EMF?
Change it.
Yeah, change in flux, VA cosine theta, with time. Now, in our particular problem, is the magnetic field changing?
Yeah. Well, we're maintaining it constant.
No. Is our magnetic field, this blue magnetic field, changing?
No, the field.
Okay, that's constant. Is my angle changing?
No.
So what's changing to make the flux change?
Area.
The area, right? So this is B, and my cosine theta was 1, so it's B delta A over time.
Overall.
Sorry. No. All right. B delta A over delta T. How do we find out the area of this loop or of this? It's only the area that's right here, right?
Oh, but I.
Say it again. It's a velocity times a length. It's a B, and I'm going to call this X. B delta X L over time. Everybody see that I have an X and I have an L. That X times L is my area here, right? Which one's changing with time, X or L?
X. X.
X, right? So this becomes B L delta X over delta T. So what does that become? BLV.
BOT.
Not BLT, BLV. Bacon, lettuce, and velocity.
That's still pretty good.
All right, so that's our EMF. Guess what? You take that and you plug it right in here and you get your current to be BLV over R, and you're done.
Okay, so we're just assuming that the delta A in that problem is when we're taking it out, not when we're adding more.
Yes.
That's what it is in that problem.
That's what it is in that
but
problem.
technically we're.
So the brown magnetic field
It
is
doesn't have enough.
this, because we're changing the area for the blue magnetic external field. Does that make sense? All right. All right, and that's actually new. That's really our last new thing. Okay? Okay, number 53. It gives you all kinds of options, and it says which ones of these will not produce a current. Okay? So here you go. Here's my loop O wire. Here's my magnet. Okay? How can I move them and not produce a current?
When they stay the same.
Yeah. I can't do this. I can't do this. I can't do this.
They don't move.
Yeah, I could do this. Right? I could do this. I could rotate this one like this. That won't change anything, right? No magnetic field change through it. So almost nothing you can do. I'm sorry, let me say that opposite. Almost everything you do will produce a current in this wire as long as the current is a loop. Now my wire is not a loop, but if it was a continuous loop, then it would produce current almost just by moving it close to it, right? Amazing. So yeah, just run down the hallway with a magnet, you'll produce current all over the place.
Wait, can we have a giant hamster wheel that's made out of
Yes.
and just run continuously?
But rotating it this way won't do anything. It doesn't change the area. It doesn't change the angle.
Okay, what if we have a bicycle thing that's making it spin around us?
Now, if you spin it like this, then you're in business. And that, my children, is how they produce electricity in our wall sockets. Is they take loops of wire and they rotate them like this past magnets. That's exactly what they do. And how do they get them to rotate?
By burning coal.
By burning coal, by burning gasoline, by burning natural gas,
By water falling.
by water falling past a paddle wheel, by a windmill turning it, okay? By little hamsters. Okay, number 21 looks like this. You have a square loop.
Wait, so what was 53?
53 is E. When you move them the same direction,
Nothing
same.
happens.
Nothing
Because
happens.
he was arguing with that. So I'm like, okay, if I leave one right here by your laptop, it's going to charge it.
No. Yeah. All right, everybody. The area of this loop is 0.2 meters squared. The magnetic field piercing through the loop is 5e to the negative third Tesla. The angle originally, no, it's going to go through an angle of 90 degrees, right? So that's delta angle change. Okay? So let's make this nice and easy. It starts like this, with the magnetic field going through, and then it turns 90 degrees. So it's going to go from how much flux to how much flux?
Zero.
Max to zero.
Max to 0. So all I have to do to find my change in flux with time, yeah, it's going to be flux magnetic initial minus flux magnetic final, and my final is 0, right? So I just have to calculate my initial flux and divide it by the time, right? So my EMF is going to be my flux over time. And that's going to be BA cosine theta over time, but we're going with the maximum, right? And so I end up with 5e to the negative third Tesla. The area is 0.2 meters squared over a time of, this happens in 0.1 seconds. And that's it. That gives you your answer of 0.01 volts. Okay? All right, how are we doing? We doing okay? All right, our last one is this one. It says you have a primary coil. Coil. With a variable resistor. And you have
A secondary coil. That's slightly smaller.
a secondary coil. So the primary, secondary. It says that this thing is turned on. They're both perpendicular to the x-axis. Says all of the following will produce current in the secondary coil except, okay, E says decreasing the cross-sectional area of the secondary coil. So if you take this one and decrease its cross-sectional area by folding it up, will that give me a change in flux with time?
Yes.
That changes area with time, right? Okay, D says varying the current in the primary coil. If I vary the current in here, does that change my flux over here?
Yes.
Yeah, 'cause that changes my magnetic field out of this one, right? That's no good. C says moving the secondary coil closer. If I move this closer, does that change its flux? Yeah, because that changes the magnetic field strength, right?
Yes.
B, rotating the secondary coil about a diameter. If I take this thing and rotate it this way,
Yeah, we're gonna.
like this, then that's going to produce a change in angle, right? Okay, so my only answer is rotating the secondary coil about the z-axis. So you take this thing And all you do is rotate it about the z-axis like this. That changes nothing, right? Same magnetic field, same area, same angle, no change, no EMF induced, no current. Okay? Shh. We're going to do a quick review and then we're going to go back to induction again. All right, magnetic field around a wire. Remember, a moving charge produces a magnetic field, and the magnetic field is in a loop around the wire, right? And it's shown by your right-hand rule. The first right-hand rule curls around. Okay, everybody real quick. This one right here. Don't say it out loud. Think about it first. Consult with your neighbor. Current coming out of the board. Which way is the magnetic field going to be?
You're doing this.
Okay, which way does it circulate? Thumb out. So there's your magnetic field. It goes counterclockwise. Okay, the bottom one is? Clockwise. Clockwise. It'll circulate around this way. All right? So let's progress to the next step. Okay, we'll start with the current. Which way is the force on this current in this magnetic field right here?
No, I'm ready.
All right, which way is the force on this one?
Down.
It's
The force. That's the one we just did, right?
Conventional currents are always positive, so which hand do we use?
Right.
We use our positive hand, right? Correct?
I'm
The right hand
tattoo
rule.
a positive sign on this.
Yeah, positive here, BIF, positive,
When I see a battery-
BIF, negative.
Right.
Okay, which way's the force?
Down.
Down. Okay, proton, which way's the force?
Velocity high. Right.
Okay, wake up.
That way.
I don't know, I haven't done it. You tell me.
Right.
To the right? Does everybody agree? No. Yes. To the right. Okay. Negative charge.
Get calling.
Yeah. Northwest high.
Okay, which quadrant does it point into? The first, second, third, or fourth?
To the second. Towards the second.
Actually, I should put this force right here, actually.
Yeah.
All right, Lisa, you're having too much fun. What's this one? Okay, quit doing this.
I'm not doing that.
Oh, I saw you.
What are you talking about?
Okay, which way's the force then? Which quadrant? First, second, third, or fourth quadrant? All right. Do we concur? All right, here we go. Down here then. This wire. Which way's the force on this wire?
Here, let me help you out on that.
I'm gonna drop something in here on my shoe.
Okay, if they gave you this coordinate system, what would you say for the force?
Negative X.
Negative X. Okay, what about this positive charge? Which way?
Fourth quadrant.
Towards the fourth quadrant, yeah. Negative X, positive. No, positive X, negative Y.
Positive X, negative Y, so it's going to be down here into the fourth quadrant. All right, what about the electron?
Down.
Negative Y.
Yeah, just negative Y.
Down. Down. Negative Y.
We've got several votes for negative Y. Do we agree? Velocity this way, magnetic field is out.
Velocity.
So negative Y. All right? Okay, what's the direction of the force on this wire in this magnetic field?
Okay,
Okay,
hold up. Maybe I'm done thinking about it.
conventional
Okay,
current,
never mind.
so positive hand,
Never mind.
current this way. Okay, this is going to be a little bit harder. Your fingers will bend around to like that, correct? So it's going to be out of the board, but it won't be maximum force, right?
Correct.
Okay, so the force on here will be out of the board. Okay, what about this proton?
Same field? Yeah, 0. Is it 0? It's at 180. Sine of 180 0.
Okay, velocity's this way. B field is this way. What's the angle in between these two?
180.
180.
Sine
So
of
what's the sine of 180?
0.
0. So there is no force. Hey, what does that mean for this proton? What's it going to do? It's just going to go and go and go.
Forever.
Yeah, it's like the magnetic field's not even there.
That's cool.
And this actually is very cool. Hey, what about this electron?
Waka, 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 waka.
All right, I agree that it is out of the board. So the force on this one will be out of the board. Now, everybody, I want you to notice something. You ready? Because this is new. We haven't talked about this yet. Does everybody see that this electron has a velocity this direction and a velocity this direction? A velocity that's parallel and a velocity that's perpendicular. Does everybody see that the perpendicular velocity will produce a force this way?
And the one that way.
And the parallel velocity will produce a force of
0.
0. So wait a minute. That means this velocity gets a force this way, which causes it to curve, right?
What?
Yep.
Okay.
Right? Right?
Okay.
Because look.
This way, you're assuming why?
It's going to get a force this way, right?
So when they just come.
And so it's going to turn this way, but when it's up this way, the force is perpendicular, so it's going to come out of the board and do this, right?
Okay.
Just like any circular motion, right? Just like this one right here, this electron gets a force down, so it's going to curve around like this, right? This one's going to curve around like this. But wait a minute. There's more. Do you see this?
Okay.
This gives you the perpendicular. But what happens to this velocity?
Keeps going.
It keeps going. Does this velocity change at all?
No.
Ooh. Okay, now everybody, watch this. What do you get when you add this motion to this motion? Okay, we don't call it a spiral because a spiral, it kind of implies that it spirals in or out, right?
Spring then?
It's technically it's called a helix. Okay? Spiral's not bad, but the technical word is a helix, like a spring. So it's going to do this. It's going to go like this. All right? Anytime the charge enters the magnetic field at an angle other than 90 and other than 0 or 180, if it's 0 or 180, it just goes straight through. If it's at 90, it'll go in a circle. If it enters at an angle, then it will helix along the magnetic field line, either with the magnetic field line or opposite the magnetic field line. And if it's negative, it will helix this way. If it's positive, it will helix this way. Now, so what? Well, we see this. Actually, we don't see this because we're too far south. The Earth's magnetic field lines go like this. All right? And charged particles from the sun, guess what? Very rarely ever hit the Earth's magnetic field at a right angle. So they come in at an angle, and what do? No. They will spiral along the Earth's magnetic field line, entering at the south and...
or helix?
Sorry. They will helix, along the Earth's magnetic field lines, entering, most of them, at the north and south pole, creating a wonderful light spectacular called the Aurora Borealis, or the... You know what the one down south is called? Aurora Australis, I believe.
Are you done?
Australian people don't like you now. All right.
don't like them.
What? Okay, we'll call it Aurora penguinus
There we go.
That's much
and
better.
aurora polaris.
Well, they're not.
Santa
No.
All right. What happens is these high-speed particles enter the Earth's atmosphere. Enter the Earth's atmosphere, ionizing the gas and causing them to glow, just like they glow in these fluorescent tubes. And it puts on a nice light spectacular in the sky. It's really pretty
Laser
cool.
rock show.
Yes. Nature's laser rock show. Okay. Tell me, do these wires attract or repel? Let's see, green wire. Green wire is into the board here, so purple wire will get,
Force down. It's into the board.
oh, into the board, so it'll get a force down. So this one gets a force down, so therefore this one gets an equal and opposite force up, so they will repel. Okay? All right, what about this one?
You do it again.
You want to do it again? Okay, this is my green wire. This is my green magnetic field. Actually, the green magnetic field comes out of the board up top and into the board below, right? Out and in. Thumb, out and in. All right? So, the purple wire experiences this green into the board magnetic field. So, purple wire this way, green magnetic field in, force down. Got it? And you can get it. Let's try this one. Okay, this point. Okay, here. Proton and electron. Alright? We'll make this my blue wire. Can you see that? Blue? Okay, what's my blue magnetic field like at point P and point E? Okay, so it comes out up here and it goes in down here. Okay, what about my yellow wire? It goes in and in, right? Because it comes out over here, right? In and out, and this one's in and out, right? Okay, so at point P, what happens to the magnetic fields? They try to cancel each other out at least, right? So it depends on
The magnitude of
the magnitudes of them to which one wins, correct?
the distance.
But this one, which one wins? Well, they both win, right? They're going in. Okay, now, there's my electron just sitting there still. My electron's sitting right there, absolutely still. Which way does it receive a force?
Well, there's no velocity, so there's no force.
Very good, because it's a trick question. The trick question is which way is the force? But unless it has a velocity, it has no force, right? Okay.
Why did we do two on that one and not only one on the first one? Like we did both wires.
Oh, I did do both wires.
Yeah, but why did we do it on the first one?
We did. Dots.
Yeah, first
No, on the
one.
one above it.
Because we just know.
Oh, this one up here? Because I just want to know the force on this one wire. No? This one I just wanted to know what the magnetic field is like here. Okay, if I ask, okay, let me ask, what's the magnetic field like in between these two wires? Okay, green one is in, purple one is also in. So you get, yeah, extreme in right here. There you go. Does that help out? Okay, now what if this electron actually had a velocity this way? Which way would the electron want to move?
This way. Right.
Yeah, that way. We'll have a force.
Yeah, right.
Which hand?
Oh.
We'll go down.
Which hand?
Which one are you talking about?
Yeah, let's go.
Electron hand, right? Your negative hand? Negative hand, velocity down. B field in. Force to the left. All right. Okay, next question. X, Y, or Z?
Which one? What?
Which way is the electric field at points X, not electric field, sorry, magnetic fields. Which way is the magnetic field at point X, Y, and Z? Okay, what's my green magnetic field look like?
Go clockwise.
It goes this way, right? So it's going to go down over here
Up.
and up over here,
And down
same,
over at Z as well, but little.
and a littler over here, right?
Well, do we know the exact equal? We're assuming X and Y are equal.
Yeah, we assume X and Y are equal. Okay, my purple. What's my purple magnetic field look like? It
Up.
goes up over here,
Pretty nicely big.
and it go over here, it goes, well, and then over here it goes
Extreme down.
down, and then a little bitty down, right? Okay? So over here it's going to be up totally, down, and over here it might be 0, right? It could be 0, depending on the distances, right? If this distance here is twice the distance of that, then it would cancel each other out, right? All right. Okay. What's the direction of the magnetic field right here? If this is a 1 amp current, and this is a 1 amp current, what's the magnetic field direction there?
Is that directly below the 1 amp?
Yes. This is a
Photon? Is it photon or just oh, it does matter.
doesn't matter. So it's a square. I'll give you these options. Option A, the magnetic field is this way. Option B, the magnetic field is this way. Option C, the magnetic field is this way. Option D, the magnetic field is this way. Uh-oh, I'm going to have lots of them. Option E, the magnetic field is this way. F, the magnetic field is this way. G, the magnetic field is this way. H, the magnetic field is this way. I, the magnetic field is this way. Oops, I. J, the magnetic field is this way. K, the magnetic field is this way. L, the magnetic field is this way. Which one is it?
I think it's G.
No, it's not B.
No,
Yeah, I'm gonna say F.
Oh, yeah.
Let's find out. Let's make this one the black one. Which way is the magnetic field do the black one?
To the right.
This way.
At the point to the left.
Which way does it circulate? Clockwise or counterclockwise? Counterclockwise, so it's going to be this way. Right? Okay, this one. It's going to circulate clockwise, right? But is it going to be the same strength as that one? Okay, it's going to be weaker. Okay, if I add these two together, what do I get?
Something really very close.
Okay, not. Which one?
Should be E.
Is it above 45 or below 45?
It should be E.
Okay, it looks like it's more E-ish, right? Because it's more that way than this way. That would be my guess. Okay? But we know it has to be either E or F, somewhere in that range, right? Somewhere in there. Now, when they give you a test question like that, they'll make it so that there's going to be one answer that has to be right. In my drawing, it's a little bit hard to tell whether it's E or F, right? But we know it's going to be in this region, right? Okay. Object shoots into a magnetic field, goes this way.
That means it's a negative charge. Yeah, it's a negative part.
It could be electron, but we know for sure it's going to be
Negative.
negative. How do we know?
Because it's moving
What's
down.
your justification?
Left hand.
Because the right-hand rule says it should go up.
But it's a lot.
The left-hand rule says it goes down.
And it doesn't.
So therefore, it's negative. Okay, now, remember, the magnetic force equals mv squared over r. That's qvb equals mv squared over r. And one of these v's cancels, and you get r equals mv over qb. Okay, that's not on your equation sheet. You got to remember how to get that, so you can find the radius. or the velocity, or something. Okay, now, next question is, I want to make it go straight. That's the path I want it to take. What direction do I make an electric field to make that happen?
Downward. Down. Because it's an electron. Make the electric field go down.
Make the positive side.
Yeah. So basically make
Okay,
it go down.
Neon, I like the way you're thinking, because this helps most students always get it right. It has a magnetic force down. That means I need an electric force up to cancel it. And for most students, you'll get it right every time if you just say, look, which plate has to go up here? I need positive up here to attract it, and negative down here to repel it. So therefore, which way is my electric field? My electric field is down. And that should make sense because my negative charge gets a force opposite to the electric field, right?
Yes.
Okay. Oh, this one first. Okay, this one right here. Tell me, what's the magnetic flux? What's my flux? Yeah, it's going to be 1.6 times 0.5 squared cosine of theta, which is 1, because it goes straight through.
The homework's retarded. I put an answer in and marked it wrong, put the same answer in and marked it right, and it was multiple choice. Yeah, and let them put the same answer in.
Excellent.
But it still took off the points for it.
Well, don't do that next time.
It was right the first time.
Obviously.
Don't insult the e-homework. It'll take points off. All right, what do we get? 0.04. Oh, my goodness. What are the units on this?
It's changing fluxes. Oh, yeah, it is
What's the
flux.
units here?
Tesla meter squared.
Tesla
Meter squared.
meter squared. Tesla meter squared. By the way, that's given a name. You know what the name of that is?
Volt seconds.
It's a Weber.
Ah.
Are we going to see
You know what? You don't have to worry about it. Tesla meter squared works great.
Thank you.
Seconds work.
Now I'm going to keep on thinking about Michigan.
Volt seconds? You have to convince me that that's the same as Tesla meter squared.
Do it.
Volts equals that over T.
Okay, maybe. All right. Now, everybody, let's say that my magnetic field is decreasing at a rate of 0.1 Tesla per second decrease.
Oh,
That's my delta magnetic field with time. It's 0.1 Tesla per second decrease. All right, everybody. Do I have a change in flux?
Yeah.
Yes, EMF equals change in flux with time. Check. So will I get an EMF?
Yes.
Yes. What will my EMF be? It will be BA cosine theta delta T delta. But which one of these is changing this time?
B.
Not the area, but B, right? So it's delta B over delta T, A times cosine theta, but my cosine theta is 1 again, right? So all I do is put in my area from before, and what do I put here?
Negative 0.1.
Negative 0.1 Tesla per second, right? And that would give me my EMF then, correct? Okay, now, but what's more important to me is, which way does the current flow in this loop?
Got no idea.
Remember, Lenz's law says that the current that will be produced will make a magnetic field to oppose the change.
Okay.
What's the change?
We're decreasing speed
The flux is decreasing.
because of B.
How do I keep the flux from decreasing? What do I need to add?
You can add more.
I need to add more.
So add more X's going in.
I need to add more. So which way do I need current to add more?
To go clockwise. The current clockwise. Yeah.
Clockwise, right? So the current goes around clockwise. Okay? Now, riddle me this. I have a loop of wire. I have a magnet. I'm dropping the magnet. The magnet is coming closer.
Catch them out again.
All right, do I have flux?
Yes.
Yes. Okay, I'm just going from here to here, right? Do I have flux right now? Okay. What's the flux look like? I've got there's my magnetic field coming out of the north end, hooking around to the south, right? I don't care about that. It's coming out of the north, right?
Yeah.
All right, so is my flux increasing or decreasing?
You're getting
Ooh, I have flux that is increasing, right?
Yeah.
Because my magnetic field is getting bigger.
stronger.
How does this loop produce its own magnetic field to oppose the change in flux? What's happening to my flux? It's getting bigger. How do I decrease the flux
Increase
then?
area? I mean, decrease area.
No, it produces its own magnetic field.
So make a
Yeah, since the magnetic field is getting bigger with time, so I need to oppose it, right? I oppose it by the loop making its own magnetic field. You can't see this, can you? By making its own magnetic field in the opposite direction, right? Does that make sense?
Yeah.
And
So if the magnetic field's getting bigger, the loop will produce a magnetic field to oppose the getting bigger in the opposite direction. If the magnetic field's getting smaller, it'll produce its own magnetic field to, in the same direction, to build it back up. Does that make sense?
so current is going counterclockwise.
So current would be going around this way. Yeah, however you want to call that. It's kind of hard to see it in a two-dimensional drawing.
Counterclockwise if we're looking from the side of the north.
All right. Here's a very typical problem. Here's my magnetic field area. I have a loop of wire. It's right here at position A, moving that way. It's right here at position B, moving that way. It's right here at position C, moving that way. It's right here at position D, moving that way. It's right here at position E, moving that way. At which of these locations is there an induced current in the loop?
It's constantly moving.
It's constantly moving.
Is it B and D?
Ask the question again.
It has to be B.
At which of these locations is there current in the loop?
It's still at 8.
Yeah, but the
They're
area
all
is
moving
zero.
to the right.
But the area is 0. So it's just B and B.
Okay, what do we need? We need a change in flux with time. So first of all, which ones can't be correct right off the bat? A and E, no current. Current equals 0. Current equals 0 because there's no flux. Okay, of the three remaining, which ones don't have a change in flux?
C.
Okay, current equals 0 because the flux is staying constant as I move totally through here, right? I'm just in the midst. Okay, now, why do I have a change in flux here? What's changing?
And changing area.
Okay, I'm changing my area. And over here, I'm changing my area. Over here, my area is increasing with time. So flux is increasing with time. Over here, my area is decreasing with time. Therefore, my flux is decreasing with time. So now, tell me, which way is the current going around this loop? And which way is the current going around this loop?
Okay, so we're decreasing area. So it's D would be going clockwise and B would be counterclockwise. Yeah, and counterclockwise for B.
Yeah.
Counterclockwise and then clockwise.
Yeah. Yes.
Flux is increasing. How do I cancel out the increasing?
By taking out some field.
Okay, magnetic field's in, so I need magnetic field out. Very nice. So what I need is magnetic field out. So therefore I need current this way. Okay, over here, flux is getting smaller. So my magnetic field is in, but getting smaller. So how do I keep it from getting smaller? I need more in. Very good. So that time the current is this way. Very nice. If you can get that, that's pretty challenging, quite frankly.
Okay.
And how do we figure out what this flux is? Remember, this is a new equation for today. This is change in BA cosine theta, right, over time. But I'm changing the area, right? And this cosine theta is 1 again. And in my area, remember I have two measurements. I have the X measurement and I have the L measurement. Notice the L is not changing, but I have a change in X with time, right? So I get BLV. Remember, L is the length that's not changing. It's the one that's going straight through. This is the length that's changing as it goes in and comes out. Does that make sense? All right. Now, this brings up a type of problem called a railgun problem. All right? Let me see if I have one in your e-homework. Actually, you know what? It's the last problem in your packet. It's like the one we just did. Okay? I'm gonna give you a different version of it. The distance between these are two what's called rails. I have a rail here and a rail here, and then in connecting them is a resistor of 5 ohms. This is a bar that can slide along the rails. Remember that thing I had out the other day where I sent current through it and it rolled back and forth across the rails? It's a similar thing. This thing is going to roll or slide this way at 3 meters per second. Okay, first question is which way does current go through the resistor as this thing moves downward? Right? Okay, so first of all, do we have flux? Yes. Do we have a change in flux?
Yes.
Which way is the flux changing? Is it getting bigger or smaller?
Bigger. It's bigger because you're increasing the area.
Ah, because where's my area?
Inside. But why are we considering this?
Okay, which way is the flux getting bigger or smaller? Bigger. Okay, so if the flux is getting bigger and the magnetic field is out, which way does this loop have to produce current to cancel out the getting bigger?
Go in.
We need to go in. So which way is current going to be?
Clockwise.
It's going to be clockwise, right? This way, right? Clockwise. So it's going to go through the resistor this way. So current is going to come around this way.
The originally was coming out, so you need to cancel out the increase?
You cancel out the increase. You need to cancel out the increase or the decrease. In this case, we have an increase out, so we need in. You add more whenever you have a decrease in flux. If you have a decrease in flux, you need to add more to it to keep it from decreasing. Right? You're opposing the change. So our change this time is getting bigger, so we want to cancel it out. If I slide the bar up, then I have a decrease in flux. I have an out flux, but it's getting smaller, so I need to add more to it. See the difference? Well, see, this is see, my area is getting larger with time. So the flux is getting larger with time. As this slides down, this area gets bigger.
Okay, wait, just one question.
Yeah.
So, the area is getting bigger, so it's going to create a current going through?
Yes.
So on the one you had is you were creating the current though, and that's why, because you're creating the current, you were probably increasing or decreasing whatever, so the area had to change based on how much you put in or out through the current.
Yes, I think that's correct. Okay, everybody, shh, we have a couple things to cover yet. Here we go. Now, everybody, when this occurs, this bar, as it moves down through here, behaves or becomes like the virtual battery. So look, if this bar is my battery, and it causes current to go around this way, what's the plus side of the bar?
This side?
Plus side?
Yes.
Minus side. And there's an easy way to figure that out. What's the bar made of?
Metal.
What's the metal made of?
Conductive material.
What's the atoms made of?
Electrons and protons.
Electrons and protons, yay!
Protons.
Okay,
So we're assuming
when the
protons-
bar moves down in a magnetic field that's out, that means protons in the bar are being moved down.
Move.
If the protons in the bar are moving down and the B field is out, won't they get pushed to the right side of the bar? I'm sorry, the left side of the bar.
Sneaky.
And what happens to the electrons in the bar? The electrons in the bar are moving down in a B field that's out. So the electrons in the bar get pushed to the right. That's how this thing becomes a battery. If I take a piece of metal, let's say this meter stick is made of metal, and I run through the Earth's magnetic field, one side will become positive, one side will become negative.
And you'll be neutral.
So put a light bulb on top of your head and connect them.
Yeah, put a light bulb in my mouth and run through. All right, now, everybody, that means current's going this way in the bar, right? Right?
Yeah.
Okay, now, this is important, everybody. Lenz's law says you can't get anything for free.
So what are we saying?
Here's how we don't get anything for free. If this would work, this would be great if we could just put this in a gravitational field and let it drop down and it would produce current, right?
Forever and ever and ever.
Nice. But look what happens. What happens to this current in this blue magnetic field?
Decrease?
Current, everybody do it with me.
Current.
Blue magnetic field.
Blue magnetic field.
Which way's the force on the bar?
Which way is the force on the bar?
Which way? Up. Oh no. Look what
Go
happens.
very far.
This thing gets a force upwards.
This thing gets a force.
Okay, stop.
So make it heavy.
And so, Lenz's law dictates that whatever is happening, whether it's a velocity or a change in flux, everything is opposed. So this motion of the bar is opposed by this force.
Okay, but it's opposed, but it's not equal to.
Well, what will happen is if it's a superconductor, it'll be equal to, and then it will stop.
So opposition is natural.
Yes.
All right.
Okay?
Oh.
Now, let me show you this, because this is really cool. All right, you see this?
You know that can't be.
I was saying
This is a very, very powerful magnet. Don't get it close to credit cards,
Or my
because it will demagnetize them. All right, it's a neodymium magnet. This cost, years ago, I bought it for $60. They're expensive. Okay, you ready?
You showed us.
with another one.
With the bolt.
$60.
That's it?
I totally buy it.
Fine.
All right. What happens is, as it falls past this copper, it produces a change in flux.
And it resists.
And that produces a current in the copper, which produces a magnetic field in the opposite direction that opposes the change in flux. And so it falls really ridiculously slow. Notice it, once it comes out,
It moves up fast.
it's normal again, right? It's crazy.
Just like my time machine that moves forward at average speed.
It's like,
It looks cooler to
Best
see it
$60
inside.
you've ever.
yeah. It's really cool when you watch it inside. It's like, all right, come on. Come on. It's not even really touching the walls.
It's low.
$60.
Yeah. $60. You're still not over that $60 thing.
Wait, did you buy it or did
For $5.
Okay, so somebody, oh, the school bus. All right, now, this one. This is aluminum.
It moves faster.
It moves faster than the aluminum. Why?
Because it's aluminum is not
Because it's not as good of a conductor.
Okay.
Now, what if I had a superconductor and I dropped it in?
Oh, exchange.
It would go whoop, and it would stop.
Yes.
Yeah.
It wouldn't move at all?
It wouldn't move at all.
How would you get it out? Gravity isn't
You could grab it, pull it out.
Push it out.
It
but it
just
wouldn't
turns
be
on.
on.
Everything affects it to the same degree.
All right, if you want to come up here and see this, you can. The other thing that's kind of weird is if you put your finger in here to stop it, and then you push it up or across in there. Actually, up's better because then it comes back out. You can feel the resistance, the resistive magnetic force.
Ooh, I want to feel it with my finger.
All right,